Okay, thank you very much for this kind introduction. So now the projectors, I think is my laptop. Yes, so welcome to this morning session. Even Angelo has arrived. So here's the plan for the lecture. It is, it's more or less a collection of thoughts. So I'm not sure if I really will follow this step by step. So the plan is, if you cannot hear me, let me know. I'm also not sure about how to work with this microphone. Maybe lower seat would be better. Okay, so the thing I want to do is I want to try to connect the ideas which we discussed during the first week for fundamental tests in the sense of testing collapse models, and then maybe also later in the sense of checking the interplay between quantum mechanics and gravity, mostly in the semi-classical regime, so connecting to André Grossart's talk, and ask the question, what kind of experiments do we have to do to actually see this? So now Angelo has already explained a lot of this. So my lecture will basically be filling this with, many pictures, animations even, so I can promise you some movies. And what I also will do is I will talk about the experiments which we do at the moment in Southampton on levitated optomechanics. Nikolai Kiesel told you yesterday about levitation, optical levitation of nanoparticles in a cavity. So in Southampton, we don't use a cavity, we do it with a simple parabolic mirror. But the things we want to achieve are very similar. So we basically want to control the motion of this little nanoparticle, we want to cool it, and we want to eventually prepare non-classical states of the center of mass motion of this particle, as, for instance, the spatial superposition state. So, as mentioned kindly by the chairman, the starting point for all this is, for me, this paper here, which we did together with Angelo and with TP, and also Kinjalk. I think Kinjalk, he should come next week, also to this conference. Again, so this paper is basically the outline, and it was very essential to setting up this conference. So you see that that talks about the collapse model, so that is the stuff Angelo told you about. It talks about underlying theories, so that is, mostly trace dynamics, so that is what TP talked about. And then it is about experiments, so how can you test this? And that is where my part is basically, as I said already, to think about how to test those models. So what are really the interesting experiments, or the experiments which are possible to detect this collapse of the wave function. Yes. Okay, so there is this Rosenfeld. He was a physicist some years ago, and he made a statement about experiments. So you can read it yourself. The essential message is that if you want to learn something new, it's much probably not it is not enough to only devise a new theory and to do mathematics. So at some point you have to test this with an experience. So you have to find an answer by experience. And he makes this comparison to the Chicago sausage machine, which cannot supply sausages if it's not supplied with hogs. And I was always wondering what this Chicago sausage machine is. And then I searched the internet and I found something really interesting. It looks like this. So that is the sausage machine. Yeah? You put in the meat here and then you press and then you get the sausage there. So, so that is the Chicago sausage machine. Okay, so I will very briefly, and at this point I always say, please don't ask questions because I don't know the answers. And you have seen it already in Angelo's talk. So that is collapse models, just to remind you what we're talking about. That is this GRW model, which was the first collapse model which was there. That was the thing where one of you asked about the Taylor expansion here. So you have the standard quantum part and then the collapse part. The important thing is that you break this, you know, the linear evolution of quantum mechanics by this collapse term, and it is an intrinsic feature of the dynamics that this is already there. Yeah, so you basically always have this mechanism, the collapse mechanism, on board on this level of the wave function. So we will later see that there's also decoherence mechanisms, of course, and if you do experiments, those are of course important because you have to somehow prevent them from happening. And these decoherence mechanisms are described in a different way. Yeah, so they are basically interactions with an environment which you in many cases can avoid. So if you do your experiment under really clean conditions, you can basically prevent those decoherence processes from happening, while the idea here is that that is something fundamental, something universal, which you cannot turn off. And you know, if the parameters are correct, and if the parameters are right, then it will appear, and you will observe the collapse of the wave function. Okay, so now, again, another slide of equations, which are more complicated. That's the CSL model. I don't know, Angelo, if you showed this. No, so you know, it gets even more beautiful, yeah, with all this here. So again, don't ask me what it is, ask Angelo. The important thing is now that there are these two parameters coming out, yeah? RC and lambda, which we have already seen in Angelo's talk. So these are the two new universal parameters of these collapse models, and the idea is, or the question is, how can you reach those with experiments? Yeah? What is it, what you have to do? And you will, you know, during this talk, again, as also Angelo already did, I will talk about so-called interferometric tests. So where you use matterwave interferometry to go in a regime to test these models for specific RCs and lambdas. And you also can do non-interferometric tests, which have basically resulted in this parameter plot, in Angelo's baby plot, to exclude, you know, models of specific parameters already. Okay, so here is my approach to this comparison between theory and experiment. And this is basically also the figure in this review article. And the idea here, it's a very confusing plot, so it will take some time to discuss this. I also always say that there are probably many more intelligent ways to make this plot, but that was the one which we did at the time. Okay, so what you do is you basically write down collapse, which you of course can do mathematically now on the level of density matrix. So you have this master equation here in the Lindblad form. So you have the typical, you know, quantum mechanical part with the Hamilton operator. And then you have this additional gamma, which basically now contains the effect of this collapse model. Yeah? So that is actually already an interesting thing, because when you write down the other decoherence models, which I mentioned already, which come from the interaction of your quantum mechanical system with the environment, yeah, you write it down in a very similar form, yeah, which means that decoherence can look very similar or exactly the same even as a collapse of the wave function in your experiment. Yeah? So that means when you do an experiment and you see that your quantum feature, whatever that is, we will define it in a minute, what actually the parameter is which you measure in your experiment to see if you're quantum mechanical or classical. So when you see that that parameter decays and that you go from the quantum regime to the classical regime, yeah, so you not per definition know if that happens because of collapse or because of decoherence. Yeah, so I think it's, at least at the moment, important to make this difference between the two things. Okay, so, you know, mathematically what you can do is you can now basically find the solution for this gamma, and you can plot this in this kind of function. And again, you have here the lambda and the RC, so the two parameters of the model, and then you make a plot, which is the red curve here, for, you know, some specific parameters, lambda and RC. So that is for this one model by Steve Adler. Okay, so now that is the theoretical part. So that is what comes from the models, and now you compare this to to the experiment, and the experiment we look into here is matterwave interferometry. So it has been, of course, already mentioned, but I want to, describe it again in my own words. So if you do a matterwave interferometer, what you do is you basically have a single massive particle that could be an electron, a neutron, an atom, a molecule, a nanoparticle, a chair, a table, yeah, and you basically experimentally you send this with some velocity to a double slit, yeah, and if everything is quantum mechanically, then you prepare superposition state in the sense that you have a probability for finding this single object in the right slit, but you have the same probability to find the same object in the left slit. Yeah? So we know that in quantum mechanics, of course, there's no mystery in this. If you use the wave function, you just calculate this. You don't really understand what's going on, but at least mathematically it makes sense. So that now you have these two probabilities for double slit, and if you then have a screen afterwards and you do an interference experiment, you see an interference pattern. Yeah? So the signature of this experiment is to see an interference pattern for a single particle experiment. So there's always a single particle only at any time at the double slit. Yeah? That's very important. So you don't have two which basically interfere there. There's just a single one. And if you have something like this, then you call it the superposition state, the spatial superposition state. I also always try to make clear that, of course, in quantum mechanics, you have many superpositions. Yes, we can have different energy states, different momentum states, different whatever states. So here it is really the position. So you have, the particle here, nothing here, plus the particle here, nothing there. Yeah? This is your superposition. Okay, so now we do this type of interference or superposition experiment with different massive particles in the constraints of the experiment. So of course, the most famous example for this is atom interferometry. Angelo mentioned this again, Mark Kasevich in Stanford. He has now an atomic fountain, which is 10 meters high. And what he's doing a so-called Ramsey interferometry experiment. So he's using light pulses to shoot at atoms, which basically go in a fountain 10 meters up and then fall down. Yeah? And what he's doing with these light pulses, he is separating, again, single atoms in a superposition state, which is half a meter of size. So it's not in the, I always confuse horizontal direction, it's in a vertical direction. Yeah? So basically, one part of this Mach-10 interferometer is higher up than the other, and the separation, the spatial separation between the two, is on the order of half a meter. That is gigantic. Yeah? If you think about this, it's a single particle superposition state, and it is of really a size which is, significantly macroscopic and large. So now, if you think about those experiments, so the data which are plotted here are not for this latest result. So that was the earlier results that had like 5 to 10 centimeters separation, and that is basically here on our theoretical curve. So if you take the experimental constraints of this atom interferometer, then you find basically a wave packet size, which now is assumed to be the spatial separation of this superposition state, so the distance between being in the right slit and being in the left slit, or being higher and lower, which is here on the order of centimeters. But you can see that because it is for single atoms, again for the discussed reason and nicely calculated example by Angelo, it is only for a single atom. So even if you do interferometry, matterwave interferometry with cold ensembles, so with, with MOTS or even with BECs, what you find is that you don't find Noon states, you find these product states. So that means that even if you have an ensemble of a Bose-Einstein condensate of 10 to the 6 atoms or so, and you do an interferometry experiment with them, you find only interferometry of a single atom with itself, if you want, out of this ensemble. Yeah? It's not that half of the ensemble is interfering with the other. So now there are, of course, many ideas how to couple the atoms in the ensemble. That is an additional operation which you have to do, and people working on this to make this Noon state. If you take the single atom, you find basically the capability of atom interferometry to measure here, which you can see is far away from RC. Yeah? So from an experimentalist's point of view, to test those models, you want to go to RC and you look into atom interferometry, then that's maybe not the best choice. Okay, so that's the first message, which is not always loved by people from the atom interferometry committee, of course. And as I said, there are many people who try to obviously create states which would scale with n, with the number of atoms, and then you would move closer to RC. So now there's the other example, and that is the systems which Nikolai explained yesterday to you. So that is optomechanical systems, which are very massive, cantilever optomechanical systems. So you basically have a mirror which is fixed, and you have a mirror which can move, and then you form a cavity of the two, and the movement of the movable mirror has an effect on the light field, of course. So you have resonances for specific modes, and the light itself has some pressure on the mechanical part. So you have this light matter coupling, which can be very strong. And you have this very massive mirror, which can be, what is it, 10 to the 13, 10 to the 14 AMU, atomic mass units, heavy. And of course, that would be very promising if you now would do a matterwave interferometry experiment with this. Yeah, if you would take such a system and you would prepare a state where you have, one in this, schematics of this experiment, if you would prepare such a very massive cantilever in a state that you have, 50% probability to be here and 50% probability to be here, then that would be really great because you have a high mass. So now the problem with this, also pointed out by Nikolai yesterday, is this one here, that the size, yeah, so the distance between the two slits in the symbolic experiment is very small. So what you do is you approximate this with the 0-point motion of the harmonic oscillator. So the idea is there that you take the standard harmonic oscillator, the quantum mechanical one. So that's something very simple, which I'm drawing now. So you have the parabolic potential, it's the energy, and then you have the energy levels. And we know that harmonic oscillator means that this is always h bar omega, and that is the n equals 0 state, and we know that the energy of this is 1/2 h bar omega. Yeah? So that also in the ground state, there is still some energy because of Heisenberg's uncertainty relation. That is the essential feature of this quantum mechanical harmonic oscillator. And if this mechanical system is now described by a quantum mechanical harmonic oscillator and is in the ground state, then it still has some energy, and this energy causes some so-called 0-point motion. Yeah? So if you now take this 0-point motion, the extent of the 0-point motion to estimate the size of the superposition state of this very massive systems, then you end up something here. And again, you find that it is far away from RC. Yeah? So to start with, it's maybe not the most promising system to try to test collapse models and to do these experiments. Of course, I have to say, and I have to mention that also this community is, of course, very clever and very vital. And many people, of course, think about, again, methods to prepare, maybe also with noon states, and also using the source of non-classical light to basically make this Schrödinger cat state. So that is, just a different name for what I said, our little double slit example, right slit, left slit. So if you now feed this with non-classical light, you can maybe make it like a really big cat, and you can go towards RC. But to start with state of the art, it's not the most promising system for this test. So now the question is, what do you find here in this regime, which is close to RC, and which can therefore test, for instance, this specific model? Then you find molecule interferometry experiments, such as those done by Markus Arndt. So if he can increase the mass of his molecules, then he can come in a regime to test those models. I will explain a little bit more about this on one of the next slides. The other thing is, of course, this nanoparticle experiment, so the levitated optomechanics. That is also something which is very promising to actually do experiments here in the sense of superposition state. So again, you know already from Angelo that there has been like a really rapid development in the field of these collapse models. in the sense that now there are really tests of some parameters, and some have already been excluded. In fact, this very model here has been excluded, as Angelo told us. But still, I would say that to do a matterwave interferometry test is still, something which needs to be done. And even if there's already a different method which has checked to the parameter range already, it is, still worth doing this superposition experiment, the matterwave interferometry experiment, to double check if that's really the case for every possible model. Okay, so that was basically the graph, the complicated graph. So that was used at the beginning to get the feeling for what type of experiments are really now able to test those models in the sense of matterwave interferometry experiments. And what you find is, basically qualitatively these conditions. What you want is you want to have a large mass in the sense of a ball or a particle which has many atoms which are bound, and you want to have a significantly large spatial separation on the order of RC, yeah? But you also want this superposition state to exist for a sufficient long time so that you can study its behavior. So these are the three parameters which you have to fulfill with your experiments, or the three criteria which you have to fulfill with your experiments to test those models. Okay, so now here's Angelo's, and maybe click to all of this. Oops. Okay, yeah, so again, you have seen this already. I don't know if that's the very latest. I think there's still something missing here, but basically that is now this exclusion plot of lambda and RC. And the two models which I mentioned before, these are the CSL models of Adler here, which have been tested by an X-ray spontaneous emission experiment in Italy, in Gran Sasso. And the matterwave experiment, so I will talk about basically state-of-the-art matterwave interferometry experiments. They're sitting somewhere here. Yeah? And now the experiment which I will talk about will basically push a little further here and will maybe sit somewhere here. Okay. Okay, so here's the matterwave interferometry experiment. So we are lucky, and Markus Arndt will be here at the end of this week. So he will basically give the whole Saturday of lectures, and he will talk about this experiment. So I will give you just a brief summary. So Markus will talk about basically a lot of the technical parts of the setup. So this is the interferometer, which is in Vienna. It's the so-called Kapitsa-Dirac Talbot-Lau interferometer. It's a very complicated name. And it basically consists of a beam. So the red line here is a molecular beam, and the molecules look like this. These are crazy organic molecules which are specifically synthesized for this experiment. And to generate the beam, you have simply an oven. So you get these molecules as a powder, you put it in the oven, you heat it to some, let's say 500 degrees Celsius, then these particles sublimate, so you get a gas phase beam of these molecules, and then you pass them through some preparation slits to confine the direction of the beam. And then you have here the interferometer that is now this so-called Talbot-Lau interferometer. So it's a more complicated version of an interferometer. And what you basically have is you have three gratings. The first grating here, the second grating here, and the third grating here. The other fancy thing, sorry, which is there is that the second grating, you see it's somehow illustrated in a different way. So that's the green thing here, that's a laser. So that's a light grating. So basically what happens here is you have a mirror and you retro-reflect the laser beam so that you have a standing wave, which has a nice pattern very close to the mirror within the Rayleigh range. And when you basically now have the standing wave, then you have an intensity profile, a light intensity profile, which is a pattern of high intensity, low intensity, high intensity, low intensity, and that you can use as a grating, as a diffractive element for these matter waves, yeah, for these molecules which pass by. What you finally observe in this experiment, in the detector here, is an interference pattern which is, the usual interference pattern which you expect. So it's a modulation of the intensity of the molecules which you detect, depending on the position of this last grating. Yeah? So again, I will not go into the details of this experiment, but you can basically theoretically calculate that if you see such a pattern, that this is indeed a quantum mechanical interference pattern, which proves that you have generated a spatial superposition state of each molecule here, and that is not just a classical shadow pattern. Okay, so now that is, if you want, the world record of this matter wave interferometry experiment. So that is the largest molecules which have shown this kind of interference pattern where people could produce the spatial superposition state. And that is on the order of 10,000, so 10 to the 4 atomic mass units. Yeah? So atomic mass units, that's the mass of a hydrogen atom. So it's like 10,000 hydrogen atoms which are combined in such a complex molecule, which are chemically linked. That is important. And you can generate a superposition state for this. Okay. There's an interesting thing. Actually, the diffraction pattern which you get in this Talbot-Lau interferometer is a so-called Talbot or quantum carpet. So if this is the position of the second grating, the light grating in the previous example, so you have basically the openings of these gratings, which are the bright spots here. And that is now a simulation which has been done by light. So you can also do experiments with light. So with every wave, you see basically this so-called near-field diffraction or interference pattern. Yeah? So if this is basically the openings of the slit, so there's basically light or matter waves coming in, then you see that there's this very complex diffraction pattern which contains a lot of information. And what you're interested in is basically this one here. So that is the Talbot image of the first order. So that distance between this image and the grating is called the Talbot distance. And that is d squared over lambda. Yeah? So for a typical matter wave interferometry experiment, so let's say C60 was the very famous first example of this. If you have the C60 molecule which propagates at something like 100 meters per second, then it has a de Broglie wavelength of about a picometer, yeah, 10 to the minus 12, which is very small. And this means that this Talbot distance here, yeah, it's about a few centimeters or something like this. Yeah. So for light, for light, it will be much smaller, so it will be more difficult to detect this. But for matter waves, because they have such a short wavelength, you get this at distances which you can manage to do a setup for the experiment of the interferometer. Okay, so I just wanted to mention this because I think it's really interesting, because you get also, I'm not sure if they're really called higher order terms, but you get basically a second Talbot image, which is not on a graph here, it would be somewhere here, which is basically at 2 times the Talbot distance. And that is now, so what you have here, so each spot here basically comes from the interference between these 2 slits here. So every next neighbor slit is basically generating the spot here. So this diffraction pattern carries the information about the diffraction between the 2. So if you're interested in 3 or more, then you have sufficient coherence, then you have to go just to higher order. So the second one here would give you the interference between, let's say, number 3, 4, and 2. So the 3 together would contribute to a single spot here. And then if you want to have 4, then you go to the next. I mentioned coherence. Of course, the most important thing here to do these experiments is that you have coherence in your beam, in your matter wave. Yeah? And the important coherence is the so-called spatial coherence, which is the coherence in this direction. So if the beam propagates in this direction or the wave propagates in this direction, then you basically want to have the coherence length, or if you want in a simple picture, that is basically a plane wave, yeah? A plane wave which hits the grating, and now it is very hard to make plane waves which are like really plane over all these gratings, but you can get waves which have, you know, a planar part which is at least of the extent of these two openings. So that means that you have a spatial coherence which is larger than the distance of these two slits. And if you have this, then you get in diffraction patterns. So if you have a smaller spatial coherence, then this extent, then you would not get any interference pattern. So in the case of this matter wave example, you would not do the quantum experiment, you would simply see a shadow pattern of this particle beam. Okay. So this is explained, again, the spatial coherence here, that is also from optics known, the so-called van Zittert-Zernicke theorem. And that is a simple illustration. So what you have is it's the same if you want to do interferometry with sunlight. Yeah? So we know that the light which comes from the sun is as such not coherent because it is emitted by many different atoms, or I don't know, whatever it is, which is distributed over the size of the sun. But still, if you collect sunlight and you set it on a double slit here on Earth, you can see an interference pattern. And the reason for this is that the sun is so far away that you only collect light which comes from a really small part of the surface area of the sun. So there is still coherence in this light. There's still spatial coherence in the light. Yeah? So if you're interested in spatial coherence, so now here's the slit, and the slit separation is this delta R, and you want to have the spatial coherence to be at least of this size, then you can play simply with the setup, with the parameters. So you can, according to this equation, usually the wavelength is given for this matter wave. For the example of C60, it is picometers, as I said. But you can basically make this distance very large. Yeah? So the R scales linearly with the delta R, with the small r. So if you make this distance very large, which is the case for Sun, Earth, then you get, you know, a significant spatial coherence. Or you can make the source smaller. So that is what you typically do in this matter wave experiments. So you make the source smaller by simply introducing a slit in front of the source. So if you have the oven, if I go back to the setup of the Talbot-Lau interferometer, so you see this thing here, which is in front of the oven. So the oven is now an incoherent source. So basically, and again, the spatial coherence is the important one. So what happens? It emits particles which fly in all sorts of directions. What you do is you place a slit here in front of the oven to collimate the beam. Yeah? So by using this slit, you effectively reduce the size of the source, and that's why you get the spatial coherence. So it's a bit more tricky in the setup. Essentially, what Marcus will tell you is that the coherence which you really need is actually prepared at the first grating, but again, I leave it to Marcus to explain all this to you. Another thing which I wanted to mention is that, of course, whenever you want to do like this beam type of matter wave interferometry experiment, you have to think about this coherence, the spatial coherence. So there's a different way you can basically collimate the beam effectively, and that is by cooling. Yeah? So that is basically why atom interferometry is so popular and has so great results, and they can even do this 0.5 meter superposition state. The reason is that they can basically effectively make the source really, really small by laser cooling, yeah? By using all these fantastic tools of manipulation of the center of mass motion of molecules. You can cool them, you can make MOTS, you can make DECs, and that effectively in this picture would mean that you make really a point-like source, so that basically every atom which comes out of this, you know, cold cloud is just moving in a straight direction. So there's basically no angle, and every atom is doing this. So that is, in that sense, also a very spatially coherent source. So that is, it's a different way. So unfortunately, that's the big disadvantage of this molecule interferometry experiments, is that for molecules, no such technique, no such cooling technique exists. So you cannot basically cool your molecules and form a point-like source of molecules to be emitted. The only chance you have is you have to, introduce this slit, and you recollimate the beam with the slit. You can see that, of course, intrinsically has a problem. The problem is that you lose the majority of all your particles, because only very few will actually go in the right direction. Only very few will generate a matter wave which has sufficient spatial coherence, which means that your detection rate in the end of the interferometer is very low. So you have to run it for a long time to collect sufficient data for your interference pattern, which means, if you run it for a long time, it's very susceptible to technical noises, to vibrations, to things which, you can only which is very hard to suppress in the laboratory experiment. So that will be better for nanoparticles. So that is the thing which I want to come to, and that is these levitated nanoparticles. So even though they're much more complex in a way, so there are many more atoms bound in this nanoparticle, it gets simpler because you have the polarizability, which is really large, which you can use as a handle, and again, you can introduce cooling techniques. So coming from the matter wave perspective, from a molecular matter wave perspective, you basically make it larger and it becomes easier to manipulate. Molecules are still, I think, the most fascinating objects which we have, but they're really hard to study because they're so complex and there's so many different degrees of freedoms which are very hard to, control at the same time. But I think there will be a lot of interesting stuff to learn if people learn how to manipulate molecules in detail, and of course all chemistry depends on this. But again, so what Nikolai told you yesterday was basically coming from the opposite direction, coming from really very macroscopic, nanofabricated structures, cantilevers, massive things, and then also you end up with this levitated optomechanics. Here you basically have the bottom-up approach, while this would be the top-down. And you see that you find, you meet in an interesting regime for these nanoparticles where it seems very promising to do, on the one side, quantum experiments, so you can prepare non-classical states, but also on the other side, it's very massive. That it, for instance, also holds promise to see some effects of gravity because the mass is so large. For the levitated particles, so, 1 million, that would be like a 10 nanometer particle, then it goes up to 10 to the 14 AMU for something like a micrometer diameter. Not at the moment, really. So, 100 nanometer is at the moment the typical size where, people learn more and more how to manipulate this. Which is, I will show you in a minute, it's still a bit large for us. Yeah? So it's still a bit too large to do matter wave interferometry in the sense of this, Talbot-Lau interferometry. But we're getting there. Okay, so let me see what I have here. I wanted to mention this, that is also very famous experiments done by Markus Arndt in the same molecule interferometry experiments, which now probe this decoherence process. So I mentioned there is, of course, collapse, which is this fundamental universal process where people assume it's there. It would be really, changing quite a lot in physics if someone would discover this, that indeed such a fundamental process is there, which is triggering the quantum to classical transition. But we know from, everyday experience in the lab that there are also other processes which do, or, trigger a quantum to classical transition, which is by interaction with the environment. Yeah? And there are many, many experiments. So one famous example is, of course, the Serge Haroche experiment. So he got the Nobel Prize for generating non-classical states of all sorts, also superposition states, and then studying decoherence processes from, letting those superposition states interact within controlled environment. And that's the same which Markus and the co-workers have done here. So you see two parts of this. And these are, always the important processes which you have to consider when you talk about decoherence in this context. So the first one is collisions with gases. So now that is this Talbot-Lau interferometer, the 3 gratings. Here's a fullerene that is in this case a little picture of a C60 fullerene, which is like an extended, that's the C70, which is an extended C60, so there are 10 more carbon atoms in the structure. And now there is, shortly after the second grating, there's a gas particle, a background gas particle, so it could be, a nitrogen or oxygen molecule in air, or it can be, whatever you introduce into the vacuum chamber. And that is now colliding, making a collision with this particle in a superposition state. So what this, in the language of, more, quantum mechanics or quantum information means is that basically this collision particle here measures the position of the superposition state, and suddenly you know if it went through, this slit or this slit or this slit. Yeah? So you basically read out this so-called which-way information. So, in a more general description of the coherence theory or, open quantum systems description, you basically entangle these two guys. The whole thing remains quantum mechanically, but this here appears as a classical state. Yeah? So that basically collapses to the one or the other option, depending on the collision event. Okay, so that means that when you do your matterwave interferometry experiment, you better avoid these collisions because you will never see an interference pattern. And that is what this plot here shows. So this shows the visibility of the interference pattern. So if you have, let's say you have your signal, which is the detected number of molecules, yeah, and you have here some kind of spatial direction X, which could be, the direction along this grating here, then you see an interference pattern. So you see here a maximum signal and a minimum signal, and then of course a measure for, if you want the quantumness of the state or if the superposition state exists, is the extent of this interference pattern. So that is, as you know, typically called the visibility, and that is, I hope I get it right, it is signal max minus signal minus, normalized by signal max plus signal minus. Okay, so if you now do this interferometry experiment and you analyze this visibility, which is plotted here, and you change the pressure in your vacuum chamber, so you basically change the number of collisions this guy makes, then you see that you lose the visibility quite dramatically. Yeah? Okay, so now there's other processes. The second most important has to do with thermal emission. So imagine now again the particle moving through this interferometer. What you do here is you have these lasers which are tuned to wavelengths so that the molecule absorbs the light. And because the molecule is such a complex structure, you have so many internal degrees of freedoms. What it means is that you absorb the photon, so you excite an internal state, but there are many, many different possibilities for the decay. Yeah, so it is not like in atoms where you have nice two-level systems and it goes back to the ground state and then you can drive Rabi oscillations and all this fancy stuff. In the case of molecules, it usually goes to some state, which means that you deposit all the photons which are absorbed inside the molecule. So that means that you heat the molecule internally. So you increase the internal temperature of the molecules by exciting a lot of internal states of the molecule. So now they have done this experiment and they have again done this with C60. And by this laser heating, you increase the internal temperature to up to 3000 Kelvin, so quite a lot. So that is very close to breaking or thermally destructing the molecule. And what then happens is that, of course, if it's so hot, then there is a very high probability for thermal emission. So simple blackbody emission happens. So this hot molecule emits a lot of photons, and also these photons basically carry information about the position of the molecule. So again, if you think about, this interferometer, then it basically resolves through which slit the particle went, and you lose your interference control. So depending on the temperature, depending on the probability of emitting photons, you lose your fringe visibility, you lose your visibility, and you cannot do a quantum experiment. Yeah. Yes. Yes. Yeah, you can do. Sure. Yes. With a potential. So, like in an electron microscope, you always give the energy, and then you have, the kinetic energy. Okay, so that, again, Marcus will much probably explain this in more detail. The important point here is now that these are decoherence processes from interaction with the environment. Yeah? So if we don't heat the molecule internally, or if we indeed cool it, then we can prevent this process completely from happening. Yeah? So we can control it experimentally. If here we don't let gas into the vacuum chamber, so if we do our experiment in ultra-high vacuum, 10 to minus 12 millibar or something like that, then for, a good number of particles, of course it depends on the collision cross-section. Yeah? So if you have very large particles, then you have to go to lower pressures because a larger particle has a higher probability to collide with the gas at a given pressure. But you have to basically prevent those collisions from happening, which you in principle can do. Yeah? So that is a process which you can avoid. So therefore, we sometimes call this avoidable decoherence processes. Yeah? But in any experiment which you want to do to see collapse models or effects like this, you have to basically do it at clean conditions that these processes are not happening. Yeah? Because in the end, these kind of decays of the visibility is exactly what you want to observe to prove that there's a collapse of the wavefront. So what you have to do, and that is experimentally very tricky, is you have to show that the visibility goes down at a certain mass, yeah, of this particle, yeah, to prove the collapse model. But you have to make sure that it's none of those processes. Yes. Now that's a good question. Thanks. The thing is that, of course, here, if you change the pressure, you see a change in your fringe visibility. If it's a collapse effect, that does not depend on the pressure at all, right? So that would not scale with pressure. The same is here. So it should not scale with temperature, the collapse effect. But of course, if you have the temperature-dependent decoherence effect, then you scale this and you see there is dependence or not. That would be the cool. Okay, so I don't think that they're terribly difficult to do. So, Marcus has done it, which means it is very difficult to do, but it's possible, it's not impossible. But what you need first is, of course, the interference pattern of something really massive where you, from the models, expect, some effect. That is the tricky part. Okay. Okay, so now I have shown you the state-of-the-art molecule interferometry, so that if you want to say the world record of matterwave interferometry. And now, of course, the question is, what is the next step, yeah, if you want to probe? Yeah. The arrow bars, oh, that's a question. So there are no arrow bars. I don't know for this one. You have to check with Marcus Arndt. Okay, so the question is, what is the next step? So how can what you need to test this collapse models is RC. Yeah, I mean, I didn't mention this, but in this type of interferometers, the Talbot-Lau interferometer, the size of the superposition state is basically the grating pitch or the grating periodicity of the gratings you use. So if you have a grating which has a distance between two slits of, let's say, 200 nanometers, then you would generate this Talbot image which has exactly the same pattern. So your interference pattern and therefore the size of your superposition state is also on the same order of magnitude. Yeah? So that is what defines the near field, actually. So that is quite promising because that is exactly what RC is. Yeah? So RC is 10 to the -7 meter, which is hundreds of nanometers. So RC is good, but the mass is still too low. So these 10 to the 4 atomic mass units molecules, as we have seen in Angelo's map, is too small to test the models. So how to make it larger? And there, over the years, are many ideas. So there is OTMA. So I will mention some of them. Nikolai, do you talk about the optical scheme, your scheme with Oriol? Yeah, okay, so yeah, you don't have to. Because I don't have the original one, I don't have it here, but you know, if you want, you can. Okay, so there's this, again, it's Marcus Arndt. You know, it's coming from molecular interferometry and building, you know, the next step, interferometer. Now you have 3 gratings again, and all of those are made of light. That's technically more advanced. Again, I don't really go into technical details to explain it to you. Now, the really, you know, stunning message here is that you can, in principle, resolve de Broglie wavelengths of, you know, something like 100 femtometers. Yeah? So that is, you know, really small. Now, the thing is that you have to, you know, put in something here. So they are playing with, you know, molecules and metal clusters, and at the moment seems to be the bottleneck to find the right source to connect to actually make a beam of sufficiently massive particles to see the interference pattern. But the machine is there. Yeah, it's built. They have demonstrated that it works with molecules which are, you know, about of the same size as in the previous Talbot-Lau experiments. But now to make the next step, they have to, you know, solve a lot of you know, technical, very demanding problems, which is to actually get the sufficient dense beam of large particles into this interferometer. And again, he will talk about this. There is a very, you know, recent idea to do this. Again, I just, you know, flick through this. You can maybe, I don't know, copy the title and then read this later if you're interested. So the idea is to have this so-called skate park. So you have one particle which is of micron size. And then it's a superconducting particle, and you use basically type 1 superconductor levitation. And then you let, you know, move this through this so-called skate park here. Yeah? So basically what you have is you have the particle sitting here, and then while it is slowly moving to this end here, you do operations with gates. So that is all, you know, very fancy superconducting technology using squids and complicated stuff like that. So you do different operations to, you know, first prepare, you know, the motional state and do some boosts and things like that, and in the end see an interference pattern of this. So that is a theoretical proposal how to do this. If they achieve to do this, this guy has 10 to the 14 atomic mass units, so that would basically test all the models, all the Colloffs models, including gravity models, Penrose-Diossi, all of it. Yeah. So if they would ever see an interference pattern here, that would basically be the ultimate test. But again, technically it's very challenging. So at the moment, I think Nikolai maybe talks about this, I don't know. Even to levitate a micron-sized particle, it's not trivial, so it is not reported in the literature that people have done this. So there's some experiments where people want to do it. If they can do it, then they have to basically, you know, prevent any decoherence, you know, process whatsoever. So now in this setup, because you're close to a chip in the cryostat, so you have vibrations and you have a lot of stuff, you have to prevent all those, you know, avoidable decoherence effects to affect your state. And but if you can do this, then you then you can test the models with this idea. Yeah. Yeah. So can you explain this?
Does it work?
Yeah.
Ah, no, it works. Just very sketchy. So when the superposition here would get pretty large until this point, and then one does something that one cannot do in optical levitation, for example. One makes a kind of unstable potential that looks like this. Right? So one would accelerate on the left and the right side downhill the parts of the superposition, and that leads to kind of this double peak structure in the probability distribution. And then they still wait for this interference pattern. They essentially rotate in phase space to see the fringes. How that is exactly done, I think, is just by weight.
Yeah.
So I'm not sure.
Thanks a lot for helping me. Okay. So that's an idea, and that I think it's really nice. So you will see that there are more ideas for those interferometers, and that is all very recent developments. That is, of course, beside the developments on the theoretical side by Angelo and others, to now say, okay, there we have to go to test those models. So these things are coming up, and people thinking about how to do it. So there are also schemes which use so-called Ramsey interferometry. So Ramsey interferometry, in a nutshell, is basically you want to control, in the application of molecular beams, which was the original case of Ramsey. But also when you do atom interferometry, you use so-called Ramsey schemes. And what you do is you basically want to prepare the center of mass motion of the particle. Yeah? So you want to basically generate the superposition state. Yeah? So you can think of a Mach 10 interferometer. So you have a beam splitter that separates the two beam paths, then you have two mirrors, and then it's reflected, and then they overlap at some later point, and then you have another beam splitter which is recombining the two. So now, in this type of experiments, you do this not with material beam splitters and mirrors. You do it by using internal states of these particles. So in atoms, you use Rabi oscillations between the two-level system of hyperfine states in cold atoms, and you prepare so-called pi/2 pulses. Yeah? So you prepare superposition states of this internal degree of freedom. But because in the case of the atom, we know that, as Zittert explained yesterday, the photons carry momentum h bar k. Each photon which is absorbed and re-emitted in a different direction has like an effect on the momentum, yeah, on the center of mass motion momentum of the big atom. So that means that there's a transfer or a coupling, yeah, between the internal state and the external state. So the internal state is the hyperfine structure transition, the two-level system, and the external state is the center of mass motion. So now, in this experiment here, which was masterminded by Sugato Bose, there are other schemes using Ramsey interferometry, but that is one example. It is the following. So now you have this big nanoparticle, which is a specific one, which carries a spin 1/2, an electron spin 1/2. So the case which is discussed here is, these famous diamonds with an NV center. So there's a nitrogen in the carbon lattice of the diamond, which is a spin 1/2 electron system. It is like a defect in the lattice structure. And what you can do optically and with magnetic pulses and with RF pulses, you can manipulate the spin. So you can do spin resonant experiments, and people do this. It's quite a big field. So now the idea here is that you use basically these two spin states, the +1 and the -1, these internal states, and couple them somehow to the center of mass motion. So the way you couple them is you have a magnetic field gradient which sits there, yeah? And if you now have a superposition state of your spin, so 50% down, 50% up, and it sees the external magnetic field, then the center of mass motion of this particle, which carries the single spin 1/2 system, is basically separated in two different directions by this external magnetic field gradient. And now the cool thing is that these magnetic field gradients can be made extremely large. So if you have a little magnetic needle, which makes this inhomogeneous magnetic field, which then of course is the gradient, that can be on the order of 10 to the 7 Tesla per meter, if you're really close to the tip. Okay, so now this is your Mach-10 interferometer. So you start here with the internal superposition state. You turn on the magnetic field gradient, and then it separates into the two, into the two different spatial positions. What you then do is, at a later point here, you send in a radio frequency pulse, which is doing a spin flip, like this. And then the same gradient is basically bringing the two together again. And then you shoot with another pi/2 RF pulse, which is basically recombining basically the two B paths, and which is erasing which way information. Yeah? So that is the important part, that you have to close with another pulse, which is another beam splitter. You have to close the interferometer to then see the interference pattern. And then you need the general phase, which in this case comes from G. So you tilt the experiment slightly so that you have an overall phase which affects one side more than the other, which basically gives you the modulation which you need to see the up and downs of the interference signal. So that's the proposal. If that would work, again, it is just a theoretical proposal. People are just about to learn how to trap these nanodiamonds. It's very complicated, and they struggle a lot to do this. They think that the manipulation of the spin is something they can do because there's a mature field of NMR and ESR spectroscopy, so they know how to play with the spin. If that would work, then that would be on the order of 10 to the 9, so that would be a viable test of collapse models, also with this idea. Okay, so now there's this idea. So now I have to say, it's one of my ideas, and I'm not sure about the idea. And I would like you to tell me if it works or not. So I can explain you the scheme, and then you tell me if that would be, like a really macroscopic superposition state in the sense of be able to test collapse models. So, again, go to the double slit experiment, have, the mass here or here with equal probabilities. Okay, so the idea is the following. You have a beam, that's the blue stuff. Could be electrons, could be atoms, whatever, massive particles. You do a matterwave interferometry experiment, you split. Yeah, so here would be the beam splitter, which could be also like in this Ramsey scheme, pi/2 pulse. Then you have these two mirrors here, which is a pi pulse. And then you send this on, a pair of this really macroscopic optomechanical systems. So there is the movable mirror, that's the fixed mirror. And then if basically this massive particle comes, then it imparts momentum or a kick to this mirror here. It moves. It has an effect on the optical field, so you can use the cavity as a readout, and you do the same in the second part. What you then do, of course, if if the particle hits here, then you know it's here, and if it hits there, then you know it. But now you do a clever thing. I think it's clever, but of course it's well known. It's the quantum eraser idea. So you basically mix the two here on this beam splitter, so the signal which comes from here and here, and you have also like an input from the vacuum. So if you detect something here, you don't know anymore if it comes from here or here. So you basically, again, you close your interferometer. So you have a beam splitter here, two mirrors here, and another beam splitter here, which is erasing which way information. If you now measure here, then what you technically do is you have something like a joint motional state here, which is like a superposition state. So now, if this would be true, which again, I don't know, then this means that you have basically these two masses, which are joint masses because of the eraser. They can be fairly, if you think about this atom interferometry experiment of Kasevich, yeah, half a meter, there could be a separation of half a meter, which Angelo tells us, of course, does not help. So if it's larger than RC, it's not important for collapse models. But still, you would have like a half a meter superposition of something which is really massive. So let's say 10 to the 14, or maybe you can even higher, like LIGO. Yeah. Okay. Yeah. So you say it's in this direction, it's not in this direction. Yeah. That's not a problem. What Tom said is that basically the important thing, or the size of the superposition state you generate, is basically not this distance here. It is basically the amplitude of the oscillation of this guy here when the atom hits it, yeah, which is very tiny. Angelo. Yeah, I mean, the diamond thing stops here, right? So you don't do the recombination part. So for the diamond, I would agree that that is like, you have basically in each of these diamonds, you have the phonons, the lattice, and then if you send in the photon, which is entangled with the other one, you basically move the lattice against each other. Yeah, so then you have also this, tiny movement. Yeah, I'm not sure. Yeah. But isn't it? Mm. Yeah. Mm. Yeah. And that's what I think, but Mm. Mm. Okay. Mm-hmm. Okay, so the reason I ask is, it's right, I'm not sure about this, yeah? I want to know and I want to discuss because the paper's out and it has been never cited. So if I can trigger a discussion now, then there's maybe more citation. Okay, Tom? Mm. Mm. Yeah. Mm. Okay, so I would say, if you're interested, have a think and let me know. Okay, so what's the time? Something like 22 minutes. Okay, so I skipped this one about macroscopicity. Okay, so now that is for me, the most important idea, because that is what we are trying to build in Southampton. And that is a nanoparticle Talbot interferometer, so we call it NaTall. So they always have female names, Otima, Merit. Now it's NaTall. So the scheme of this interferometer is here. So the idea is to start with a single nanoparticle in an optical trap. Yeah, so it could be, something with Nikolai showed you yesterday. So you have this particle and you cool the center of mass motion. And again, as I told you when we talked about the molecular interferometry, the important thing is the spatial coherence. And now with these nanoparticles, because they have such large polarizability, you can couple light to it and you can do some cooling cavity or parametric or other means, and you can indeed form a point-like source for this. So you can make that the matter waves associated to this guy are plane when they hit the grating, at least for the extent of 2 openings. Yeah? So the temperature for the center of mass motion which you have to reach for this is 10 millikelvin, which should be somewhere here. So that is a temperature which is feasible. So people have done this, have reached these temperatures for this optical cooling. What you then do, you simply turn off the field, which is not as trivial as it sounds. So you have to do it in the right way, so that you don't give a kick to the particle when you turn off the trapping field. But anyway, so that's possible. People do this with cold atoms, for instance, in these fountains. So you drop the particle, again, through a grating, which is made of light. So it's a phase grating. Here's the mirror, retroreflection. What you see is the intensity profile of the standing wave. Again, you have high and low intensities, and then the matter wave is diffracted there if the spatial coherence is at least as large as, the distance between 2 of those intensity minima or maxima. Okay, so then you do it with a single particle. It goes through. Here you prepare the superposition state. Then the superposition state evolves, so you need a minimum distance to see the effect. And then what happens is that the particle basically gets detected by simply landing on a glass slide. Yeah, and you have basically one click, or one detection, one data point. Then you have to repeat this with very many particles, so 10,000, 100,000, a million, which is another very demanding part of this experiment. And then you basically have this distribution of particles at some point. You use optical techniques. This is a glass slide, so you use optical scattering techniques to resolve this individual particles. So that is also technology which has been developed in nano optics. So you can simply Rayleigh scatter light from each of those particles, and then if you do clever image processing of the intensity profile of the scattered light, you can localize the particle by, good enough so that you get position resolution to see individual particles, and then you basically do a movie. So you basically drop a particle, you measure where it is, you take the image, then you drop the next particle, you measure where it is, you use the previous one as the background subtraction for the next one, and then you go on, and hopefully what you see is an interference pattern. Yeah? So that basically in the position distribution, so if this would be basically the view through the slide from the bottom, so you hopefully see something which looks like this, where each of those dots is now one of the single 10, 20 nanometer particles. Yeah? So you see that they're, somehow arranged in an interference pattern. So you have regions where you have, a larger concentration, you have regions where you have almost none, and then you have larger again. Now the structural size of this should be, again, a copy of the grating. So if you have 200 nanometers grating period here, you also have 200 nanometers between those maxima in your detected particle distribution. Again, so that is using the Talbot effect is also in a near field. So again, you get this beautiful carpet, and the interference pattern would be now basically, which you measure here for a given position or dropping time, would be a cut through this quantum carpet. And then you have, high maxima, low maxima, high maxima, low maxima. And now there's, again, you can calculate this. You use, Wigner functions, which, I guess some of you have heard about, which is the standard way to calculate basically this, what happens to the matter wave here. So you calculate the quantum carpet, but you can at the same time also calculate the classical expectation. So also if you drop particles and there would be basically no superposition state here, then you get the distribution, which maybe could look similar like this, but the important thing is that you have, for instance, here you have this phase shift. So if you measure basically your interference pattern here at this cut, which is a certain distance between the grating and the slide, then you get an interference pattern which has the maxima and minima at certain positions. If you then look for like longer dropping times or larger distance between the grating and the slide, which would be here, then you get basically a phase jump, which is a typical signature of a diffraction. So you only expect this in the real quantum carpet. So in the classical analog, these lines would be basically really straight, just like classical trajectories of the particles. No, I mean, the free grating Talbot-Lau, so OTIMA, for instance, is not restricted for these masses. So you could also do these masses in the OTIMA, and that is, of course, what Markus Arndt is doing. So we're talking here about, 1 million to 10 million atomic mass units. Yeah? The idea of this is to try, a completely different technology. Yeah? So in Markus Arndt's experiment, you always have this beam source, which emits a vast amount of particles, but they're in all sorts of thermal distributions. So you have to select, and you, in the end, have very low detection rates. So it's not that you use preparation techniques which are known in quantum optics or in cold atoms or in optomechanics. Yeah? You basically come from a completely different field, technologically. Yeah? So just from the techniques you use. So the difference here is that you basically, what we try to do here is we just take a single particle and we try to prepare it carefully by cooling, yeah, and then drop it through a grating, and here we prepare, if you want, this non-classical state or the non-Gaussian state, which is the superposition state. Not, here is the optomechanical part, which uses fancy kind of quantum optics procedures, yeah, or could, if there's a cavity. Here you use basically the stuff which Markus Arndt also used. Yeah? You prepare the superposition state in the classic sense of matterwave interferometry, so you have a grating which acts as a beam splitter. And then you do the detection. In that sense, it is really, as I said, so you have the bottom-up approach and the top-down approach, and that is where it somehow meets. Yeah? So you borrow basically technologies from both. So the thing was that when I started to think about this, so I did it exactly in this way. So I thought about, okay, so if you have this particle, how can you collimate this? And then, of course, cooling came up, and there was Oriol's and yours, the first proposal for doing a similar way, but using a cavity and then a certain, quantum optics operation to prepare, so with a double well, to prepare the superposition state. And I was sure, just using very simple estimates that would work, but I could not calculate this. And then only when James Bateman joined the group, he was clever enough to learn Wiener functions, and he could basically do the calculations, which is then, the way you convince others that it works. It's just a different approach. It's just, we will see who wins. Okay, so now what we also have done for this proposal is basically to check these avoidable decoherence processes. So again, gas collisions and thermal emission processes. So for a 10 to 20 nanometer particle, it is feasible to, for instance, do this experiment with the particle to be at room temperature for the internal temperature. So the inside of the particle is at room temperature. And for a 10 to 20 nanometer particle, that means that there is basically, not sufficient thermal emission for the duration of the experiment to decohere, to thermally decohere by blackbody radiation this particle. So that is very, very important, because at the moment there's basically no, there's one technique, which is just attach it to a cryostat, which cools everything, but there's no other technique where you can basically cool the internal degrees of freedom of this particle. Yeah? So you can, by these techniques, which Nikolai explained to you yesterday, and also by parametric cooling, you only affect the center of mass motion. Yeah, so you can make it to, millikelvin for the center of mass, but the inside of this particle is still, very hot, 300 Kelvin, or maybe even higher, because you always absorb some photons which heat it. So we did this, and actually what turns out to be the limiting factor for this, for this mass here, so you could ask the question, why don't you go for something larger? The limiting thing is really Earth's gravity. So of course we drop this particle freely, so it's in free fall. And now we know from Galilei that basically the acceleration is the same, yeah? For all particles. But the point is that if you have a particle which has a larger mass and it is at a certain velocity, let's say after a specific, dropping time, then of course the larger the mass, the smaller the de Broglie wavelengths. Yeah? So there's inverse scaling with the de Broglie wavelengths. And the de Broglie wavelengths is, in the end, the thing which you have to resolve in your interferometer. So the way you do it is you make the distance between the grating and the detector larger. So So now you can easily calculate if you just use, kinematic equations. So parabola mechanics, basically, that if you want to do this experiment with 10 to the 8 atomic mass units, that this distance is something between 10 and 100 meters. Yeah? So that is somehow approaching the, very expensive scale, at least, right? So if you want to build an interferometer, so 10 meters they have done in Stanford, but if you want to do it for like 100 meters, then you need to have really a very convincing argument for funding agencies to allow you to build such a thing. So, yeah. Yes, so that's a very good point. Of course now, and that is the essential idea of the skate park by Oriol Romero Isard, which I showed you before. So of course you can compensate for the free fall by just having a field, yeah, which is basically supporting, levitating the particle. So you have some sheet of, could be light, could be magnetic, could be an electric field, and now the particle sits there, and then you do the interferometry just in the propagation direction there. Yeah, so you let it go slightly, and you do interferometry in this direction. So now the problem with this is, and I mean, Oriol much probably has found the only way where it is, feasible to be working. The problem is that if there are any ripples in this, potential, yeah, that of course is again measuring which way information. So you have much probably a stronger effect from, fluctuations of the electric field, which is basically making this to your supporting shield, and then the particle is not freely moving in the direction where you want to see the interference. So that's a problem. The other problem with charge is, so if you have a charged particle, then of course, Coulomb interaction or, all sorts of interaction which couple to the charge, there are very many, and they're very strong. Indeed, and that is an interesting example, there's only, for charged particles, there's only electron interferometry, and then there's helium plus interferometry. So Franz Hasselbach in Tübingen, he did this many years ago, and it seems to be very hard to increase the mass of the ion for interferometry. There's of course ion trappers like Dave Wineland, they have done cat states or superposition states in Paul traps, in ion traps, but those are very tiny, and what you do is you trap a single ion and then you do, again, quantum optics like operation very similar, or basically, that is the stuff which we now borrow in optomechanics from ion trappers, is they then separate the cat, but the cat is very small. So now if you do like this free beam ion interferometry, then there are all these decoherence mechanisms which come from coupling to the charge. Yeah? So it seems that the escape for electron interferometry, for instance, is that it is so fast. Yeah? So the electron is moving so fast that it is not coupling to this, faster than any decoherence mechanism. And there are also studies, again, by the same guy, Franz Hasselbach, who has basically slowed down electrons in his interferometer, and he could see that there was, for instance, a mechanism when you have a metal plate and the electron is flying over this and you change the velocity, then at some point the electron couples to the image charge, and this interaction also, reads which way information, and you lose your fringe visibility. Okay, so that is the thing we are building. So I will, much probably next time, 7 minutes, I will talk about this part, so the trapping, how we want to do the trapping for this interferometer. We also have the setup, the vacuum chamber for this, and now, step by step, we plan to build the interferometer. That's an ongoing project in Southampton. Okay, so now that is the other possibility, which is called MAQRO. And that is actually, again, for the same reason of gravity. So you go to an environment where you have basically no gravity or very small gravity. You do it in space. Yeah? So you do this, this same interferometer or something, similar on a space platform. And there's a proposal for this. So Rainer Kaltenbeck, also in Vienna at the moment, is leading this. So the idea is to, at the moment, to take something that is the LISA Pathfinder module, so the thing which is already up there and which is like 2 or 3 months ago, it has the spectacular results that they can very nicely stabilize the position of the satellite by this drag-free motion control. So to take this platform and assemble a matterwave interferometry experiment there with the massive particle, and then of course, if you have almost zero gravity, then you can, do the experiment with much larger objects. It is also, of course, difficulties. There are other difficulties like, thermal heating from the sun, from the module, and things like that. But in principle, the particle is not moving. You can simply prepare it in spatial coherence. Then you give it a little kick and it moves really slowly, or you keep it at the same place and you just see how the superposition state evolves. There are also ideas together with André Grosshardt actually to use this kind of platforms for Schrödinger-Newton tests, because there also you want to study the wave function expansion for a long time, which is prevented on Earth, again, by the same, problem of, dropping in gravity. So you could also, test Schrödinger-Newton models on this. There is a larger consortium, or let's say medium size, so 40 people, and their research groups are involved in this and putting in one proposal after the other to ESA to convince ESA to actually fly this stuff. Yes, there's also, I should mention this, there's a cost action. And Angelo is the boss of the cost action. It's called QT Space. And QT Space basically is there to try to understand and learn what is actually needed to bring, a quantum experiment such as a matterwave interferometer into space. Yeah, so it's a very complicated thing because it's really, really expensive. We're talking about like $1 billion, I don't know, the units don't count anymore, dollars or pounds or whatever. So, you have to convince a lot of people from, governments, funding agencies, scientists to agree on, doing this experiment. It's basically, the effort in this QT Space action, which is at the moment a European action, to understand how to do it. Huh? MAQRO, that's macroscopic quantum resonators. And again, the origin was, by Markus Aspelmeyer's group together with Oyol, Homero Isard, and Nikolai is involved. And it's really, so most of the people who working with these levitated optomechanics or matterwave interferometry are involved in this. It's like a community effort. But on the other hand, of course, we have to be fair to say if the other idea of the magnetic skate park, if that works, if you can find basically on ground an experiment where you can levitate the particles so that there is no field which is disturbing the superposition state, then it would not be necessary to do this particular experiment in space. And that is, one of the points which has to be sorted out. Is it possible or is it impossible to do these kind of really high mass matterwave interferometry experiments on Earth, or do we have to do it in space? Okay, so I don't know how many minutes. 2 minutes. So I think I would stop here because the next is to talk about levitated optomechanics. I'm much slower than I was planning. But that will be about the experiments, and I do it next time. Yes, yeah, you can do this, and there are some experiments like this. So people do drop tower experiments. So there's a big drop tower in Bremen, which is, what is it, Andre, 100 meters or so? 150. So it's basically, it's a long tube which is evacuated, and there's a module which they first shoot up, and then it falls down. So they have like 10 seconds of free fall. So now 10 seconds is a very short time, right? And then also, because you can imagine that it is technically highly demanding to have, I think the module which they shoot up and down is something like 100 kilograms or so. So they can only do it one per day, one of those up and downs per day. So if you want to do an experiment with many particles where you need the statistics, so I think the first challenge would be to have one sequence in 10 seconds, which is, okay, so the cooling and the dropping and all this of the particle, and then you would need to repeat this 10,000 times and a million times. So That's challenging, but it's not impossible. So someone has to come up with a clever idea. So if you, for instance, would be able to do the experiment not with one particle, but with many simultaneously, so that it's like a one-shot experiment, and they all fall like simultaneously and then form an interference pattern immediately, that would be quite cool. Yeah? And then, drop tower would be possible. The other experiments which they do, and the atom interferometer guys, yeah, so they are working on bringing an atom interferometer in space. So they want to test the GR, so Lorentz invariance, and the equivalence principle, these kind of things. And they already have done drop tower experiments. So they have shown that you can do a BEC, you can form a BEC in free fall, and they also think they have done matterwave, not 100% sure. Then there are other funny experiments where they do, so they are so-called parabola flights. So they have an Airbus 300 something, which is going like this, and it's really dramatic. And they put the experiment inside, and then when you hear and when you hear, you get free fall conditions. That's, by the way, where they shoot all the movies where you see them like, without gravity, moving without gravity. So there's a funny story. There's one of those Airbuses in Bordeaux in France where they just do experiments, and they have done also cold atom experiments on this. There's one student who was doing it the first time, and they say the first time is really always interesting. So because you cannot take it. So he was getting really sick, and that was fine. No one expected it differently, and then they said, okay, it will be better the second time. And the second time he was, approaching the aircraft, and while he was just looking at the aircraft, he was getting sick again. Yes. Huh? Yeah, of course, yeah. It's pilots, everything, and then also the scientists, they're inside and control the experiment. It's really funny. Then there are other ideas. So in Hanover, for instance, in Germany, they want to build the so-called Einstein elevator, which is like a drop tower, but it moves not over 150 meters, let's say, maybe only 10 meters, and it moves up and down much more often. So it's more like a big up and down shaking thing. And then you can also have a longer time of free fall where you can do experiments. There's another experiment which they also do on sounding rockets. So that is somewhere in Finland, where there's only woods. Yeah, and they have a launching base for these rockets, and they put the experiment on the rocket, and then it also goes up, and it also does a parabola flight. And I don't know what times for experiments they have, but there was a very big problem they had, and that was with the launching base. So that was not really stable. And indeed, the first rocket they shoot, it went in a completely wrong direction. And they were really lucky that it was not in a highly populated area. Yes, but they're also doing these experiments. And I guess if you want to go to space with any of those, then you have to do all this kind of tests as a kind of technology check. Yeah? You have to basically, before you go to space, you have to show that the experiment works in the aircraft, in the drop tower, in the sounding rocket, and that it survives and that everything works. And then you maybe get the mission granted. Okay, so that's it.
One of which full gravity is acting, and on another one, it is a decelerated system. And compare the results of those two. Why?
You mean you do two matterwave interferometry experiments,
Yeah.
then you compare the two? Yeah, there are ideas doing this, but while you can of course think about this and you can calculate it, it's really, at least for massive particles, very, demanding and critical to do. They do this with cold atoms, where they have like two particles of different masses, and then they have done tests, Andre, right, of how is it called, universality of free fall, or with cold atoms, like dropping experiments. They have two different species, two atoms which have different mass. Yeah, okay. So, but there are ideas, and I think, again, atom interferometer people are much more advanced in technology, so they can do this. think they have done it in a drop tower. There was a paper by Ernst Rasel on universality of free fall, and I think it was not the proposal.
Okay, then if no question, thanks the speakers.